All right. Thank you, Belicia. Welcome, everyone. Thank you for signing up for the short course. I hope you have had a good week so far, participating in all the other courses of the winter school. I hope it was useful, and we hope today's will also be useful. I'm Narayanan Rengaswamy. I'm an assistant professor in the Department of Electrical and Computer Engineering at the University of Arizona here in Tucson. I'm in my fourth year right now. My primary focus is on quantum computing and networking, with a specific focus on error correction and fault tolerance. That's what I do for my research. So I will be co-teaching this course with two of our excellent grad students, Michele Pacenti and Sijie Cheng. So I will let Michele and Sijie introduce themselves, and then we'll get started with the course. Go ahead, Michele.
Thank you, Narayanan, and hi everyone. Welcome. I'm Michele. I'm a PhD candidate at the University of Arizona with Dr. Banevasic, and I do research in quantum error correction and quantum LDPC codes. Um, Sijie, leave it to you.
Okay, I am Sijie Cheng, and I'm also a PhD candidate working with Professor Rengaswamy and focusing on the distillation based on the quantum error correction.
All right,
Yeah,
great.
yeah,
So we can get started with the course. So Michele, if you want to share screens. So Michele will
Great.
be teaching the first part of the course, and then I will teach the middle part, and then CG will finish us uh, towards the end.
Okay, so I'll be introducing classical error correction. Um, so let's get started. And we start with a very high level thinking of what is error correction. So now you see on the screen this sentence, and of course you can see that there are some errors. In particular, we have some erasures here, but somehow we are still able to uh, somehow collect back the meaning of this sentence, right? It's not difficult to see that this sentence is typing is no substitute for thinking, which is a quote from Richard Hamming, which is a figure we will see uh, later through this course, a very important researcher. Um, so basically, you saw that the sentence had errors, but we were able to get it back and at least to get the meaning back of it. And in fact, we are able to do this because human language is a subset, the words of the human language is a subset of all the possible sounds that a human being can produce. So if we denote with S the set of all the sounds that human can produce, and then we take a subset called L, which is we define to be our language, and then we have, the complementary set, S minus L, which is all the sounds that are not belonging to the language. In this case, the example that we saw, we could say all the words not belonging to the language. And of course, those words on the left, uh, those affected by the errors, actually don't belong to the language. But we are able to get them back to their nearest neighbor word. So basically, what is the word belonging to the language that is actually similar to this? This is typing, this is substitute, this is thinking. Notice this could also be thanking, but then given the context, we're able to say, oh, this is thinking and not thanking. So this is, we will see it more formally later, but this is basically what we call maximum likelihood decoding, which is again the act of taking the nearest code word, as we will see, the nearest word belonging to our language to be the right candidate for our decision. So, given that human beings use error correcting codes every day and that the human brain actually performs decoding all the time without you even knowing it, we want computers to do the same thing. Except that computers now don't use the alphabet, don't use the Latin alphabet or the Arab or the Cyrillic alphabet, but they use basically 0 and 1. And so uh, we define the binary field. We will use this notation here to define it. So we are talking about vectors with n elements. Each element of the vector can be either 0 or 1, and we define addition and multiplication with the tables. And also, we assume that words in this language that we are defining for our computers are independent, which is different from what actually happens in the human language. But it would be sufficient actually for us to correct errors. And so, just like we did earlier, with all the sounds that the human can produce, now we can consider all the possible binary vectors of length n, which of course are in total 2 to the power of n. And now we can take a subset uh, of these vectors and define them to be our language, our code. Particularly, we want 2 to the k vectors, and we say that these vectors belong to our code C, and therefore all the other vectors won't belong to our code C. And of course, it follows that k should be less than n. So now there are specific choices. How do we choose these 2 to the power of k code words of our code? Um, an example of how can we do it is given by the repetition code. So this is the most simple and intuitive example of error correcting code, um, which basically means whatever you want to say something, repeat it many times until someone can understand what you're saying. So first of all, let's understand what this 313 means. So in general, this is how we characterize an error correcting code with this triple of numbers, NKD. N is called the code length or block length, and is basically the number of bits uh, of code words. So basically the words of our language are vectors of length n. K is called code dimension, and it's called dimension because the code contains 2 to the power of k code words. So basically, it gives you the size or the number of code words of your code. And D is called minimum distance, uh, where distance is Hamming distance. So Hamming, again, the one from the quote of earlier. So let's define what is the Hamming distance. So consider the code words of the repetition code. The repetition code has k equal to 1. So it means that you only have 2 code words, and these code words are the all 0 code word and the all 1 code word. So basically, if I want to send bit 0, I send 3 0 bits, and if I want to send a bit 1, I send 3 1 bits. And the Hamming distance between between a pair of code words is the number of positions in which the two binary vectors differ. So in this case, we can see that the first position is different, as well as the second and the third. So the Hamming distance between these two code words is 3. And D is the minimum of all the Hamming distances between all the code words. For the repetition code, we only have 2 code words, so we only have one D, which is tautologically the minimum also. And so now what happens when we have an error correcting code? It happens that the space of all the possible binary vectors, in this case of length 3, in general of length n, is partitioned into what are called Hamming spheres or Hamming balls. At the center of each sphere, there is a code word. And then in each sphere, there are binary vectors not belonging to the code, but that are close to that specific code word. So for instance, we can see here that associated with the all 0 code word, there is 001, 010, and 100. So basically all the vectors with Hamming distance 1 from that code word. And similarly here, you can see that 110, 101, and 01 are at Hamming distance 1 with the all 1 code word and Hamming distance 2 with the all 0 code word. So basically, we pack the whole space into spheres, and you can consider each sphere as a coset, and each code word is a coset leader for that coset. And we will see now why this matters. And each aircraft code can correct T errors, and T is equal to floor, so this is basically the smallest integer uh, close to this number, D minus 1 by 2, when D is odd. So in this case, the minimum distance is 3, so we can correct one error. And we will see an example just in a moment of how the repetition code can correct actually errors. We also define the code rate, which is the ratio of k over n. So of course, if the rate is close to 1, it means that n is just slightly bigger than k. So we are not using a lot of additional bits. So for instance, k is equal to 1 in this case, and n is equal to 3. So for each bit that we want to transmit, we add 2 bits of redundancy. So the rate is 1/3, which is not that high, but not even that low. And of course, we want the rate to be as close to 1 as possible, because it means that we're not using much more resources compared to what we would do without using the error correcting code. Okay, so basically we add redundancy bits to protect our information. But before seeing how actually we are able to protect information, we have the first poll question. How many redundancy bits are used in a 155.10.21 code? And how many errors are guaranteed to be corrected by the code? And how many code words does the code have? So you have these 4 options, and of course, one and only one would be the correct one. And by the way, these parameters, 155, 10, 21, are not just random parameters. This is a very, very, very famous code, um, which is called tunnel code. Okay, so we have the results, and most of you have answered correctly, the 43%. We have 145 redundancy bits because for each 10 bit of information, we add 145 redundancy bits, and in total we have 155 code word bits. And it can correct 10 errors because if you recall the formula, you have 21 minus 1 divided by 2 is equal to t. And you have 2 to the power of 10 code words, which is 1024. Okay, so before we can understand how we correct error, we have to model how actually errors happen. And usually this is done through what is known as channel. So imagine that you send your bits through the channel, and the channel does something to your bits. This is the idea. And the channel we're going to consider here is called binary symmetric channel. So if you send a 0, you have probability alpha of it being flipped to 1, and probability 1 minus alpha to not being flipped and to basically remain 0. And similarly, the same happens to 1, so that's why it is called symmetric. And so you see that if I transmit the all 0 code word, the probability of having one single error is given by alpha, so the probability of having one flip, times 1 minus alpha squared. So probability of having one flip times probability of not having the 2 other flips. And similarly, the probability of having 2 errors is alpha squared. So probability of having 2 flips times probability of having not having the other flip. And probability of having 3 flips is simply alpha cubed. So since alpha is obviously less than 1 because it is a probability value, the most likely error is always the one, the single error. And the concept of most likely error, as we will see, it is very important. In general, we can define Hamming weight to be the number of ones in our code words or in a vector. So in this case, we have Hamming weight 1, Hamming weight 2, and Hamming weight 3. And the most likely error is the one with the smallest Hamming weight. Okay, so let's see how the repetition code can correct errors. Imagine that you send the O0 code word, and now your binary symmetric channel flips the bit in the middle. Now you simply consider, if you recall from earlier, how the space is partitioned with the Hamming balls. And you say, well, um, the vector 0, 1, 0 belongs to the Hamming ball of 0, 0, 0. So it means it is closer to 0, 0, 0 than to 1, 1, 1. So what does it mean? If I had transmitted 0, 0, 0, a single error could have generated 0, 1, 0. While if I had transmitted the old one code word, I should have two errors to get 0, 1, 0. But as I said earlier, having one error is always more likely than having two errors. And so the most likely code word that I have transmitted should be the O0 code word. So now we have the second pull question, and assume that we transmit the O0 code word, but then the channel introduces two errors, and the received sequence is 110. So now, what is the output of the maximum likelihood decoder? What is the most likely transmitted code word given this received vector based on what we said earlier? Um, so the poll question should pop up soon. There you go. So basically, the maximum likelihood operation is always to map back the received binary vector to the closest code word. There you go. 57% of you answered correctly. Of course, the decoder will say, well, 111 must be transmitted because of the same reasoning that we said earlier. So now you see why the 313 repetition code can only correct one error. Because as soon as you have two errors, your decoder will commit a mistake. And there's nothing we can do. Uh, because this is the ideal decoder. There's nothing we can do better than this, other than increasing the minimum distance of the code. And in general, this is a nice picture uh, of it's a visualization of the Hamming spheres. Of course, here they are not represented as spheres. It should more correct to call these as Voronoi region or decision regions. So basically, each red dot is a code word, and the white dots are the vectors not belonging to the code. But you see that each vector belongs to the Hamming ball of one code word. And so this is, I don't know, a better representation of how actually it would look like when you have a code with many code words. And the maximum likelihood decoding is just saying, well, what is the cosset leader, what is the code word that corresponds to this region here, given that I received this specific vector. And now we can formalize this mathematically. So let's define D to be the Hamming distance between two binary vectors x and y. And now we know that for the binary symmetric channel, the probability of y given x, so the probability, basically the flips introduced by the channel, is given by this expression. So we have D flips, and we know that each flip happens with probability alpha, while all the others are not flipped. since the vector is long, has n bits, I will have n minus d non-flips. And so basically we want to find x hat. X hat is the estimate for a code word. And the maximum likelihood estimate is the code word that maximizes this p of x given y. So given my received vector y, I want to pick x that maximizes this probability. And now we can use Bayes' rule to write p of x given y in this form. It is convenient now. So since p of x does not depend on the received vector, we can rule it out. It is sufficient to maximize p of y given x. And it is convenient also because of this form to maximize this logarithm. So we consider log 2, the base 2 logarithm of p of y given x. The exponent here, we can bring it down. So we have d log of alpha plus n minus d log of 1 minus alpha. And remember, we want to pick x that maximizes this expression. But d is a function of x. Alpha is not a function of x. N is not a function of x. So now we can write d log of alpha divided by 1 minus alpha plus n log of 1 minus alpha. This factor does not depend on x because it does not contain d, so we simply can discard it in the maximization. This logarithm is negative because alpha is less than 1/2. So maximizing this means minimizing d. So this simply means that the maximum likelihood estimate is the code word at minimum Hamming distance with a received vector, which is basically what we saw earlier in our example. And this is how we formalize it mathematically. So given y, a received vector, I go through all my code words and I pick the one with smallest Hamming distance, and that would be my best possible estimate. Okay, and a very convenient way to represent codes, linear codes, um, which is linear codes, basically what we talked about till now is linear codes, uh, which is by far the most important class of error-correcting codes. Linear codes can be represented as matrices. So we can use linear algebra to study error-correcting codes. So let U be a binary vector of length k. U will be our information vector. So basically the binary string that I want to send. And let G be the generator matrix of the code. And I will introduce just in a moment a generator matrix, which is simply the matrix such that U times G, basically the result of U times G is a code word. So basically G is a matrix that I can multiply any binary vector that I want to transmit, and I get a code word. The dual of the generator matrix is called parity-check matrix. This is a little bit more complicated to understand at first. So H is a binary matrix such that each time I multiply X is a code word, times H transposed, the result is always 0. So in other words, we say that X is in the image of G, or in the row space of G, and at the same time is in the kernel or the null space of H. And because of this, because all the rows of G now are code words, and all the code words are linear combinations of the rows of G, it follows that G times H transposed is always equal to 0. So now let's see how these matrices look like for the repetition code. K in the repetition code is equal to 1. So U will just be 1 bit, 0 or 1. So we need to define a matrix such that 0 times G is the O0 code word, and 1 times G is the all one code word. So simply G is 111. It's actually trivial. Less trivial is to find the parity-check matrix. So one can do it by hand and see that it will actually look like this. So the parity-check matrix has n columns and n minus k rows, while the generator matrix has n columns and k rows. You can verify that G times H transpose is equal to 0. In fact, you can see this as simply summing the columns of H, of course, over the binary field. And so in the first row, we have 1 plus 1 plus 0, which is 0. And in the second row, we have 0 plus 1, which is 0. And now we can use actually, it turns out that the parity check matrix is much more important for an error correcting code, especially for LDPC codes, as we will see later. And we will use that kind of representation to define a code. And the parity check matrix can be used to compute the error syndrome, which is also a fundamental concept in quantum error correction. So as soon as we have a code word, we transmit it over a binary symmetric channel. Now, the bit flips that the channel introduces can be modeled as an addition. So the received vector can be modeled as x, which is our code word, plus, and this is a plus over the binary field, an error vector e. And now the syndrome can be computed with y times h transposed. Y is equal to x plus e, and now we can use the associative property. But we know that because x is a code word, this product is 0, and therefore S, the syndrome, will only depend on the error. And so there is a linear mapping between the error and the syndrome. So for example, let's assume that, again, we have our 313 repetition code. We transmit the O0 code word. And we have a flip on the first bit. And so our received vector is 100. We compute the syndrome, computing 100 times H transposed. It will give the vector 10. And now, given the syndrome, we can get back the most likely error and the most likely transmitted code word using what is called the standard array table. So in the standard array table, we have 2 to the n minus k rows and 2 to the k columns, plus 1 columns. So in the first row, elements in the first row are all the possible code words. And the last column, we have all the possible syndromes. And what's in between are all the possible errors that can happen. So how do we use, so the standard array table actually implements the maximum likelihood decoding. So we compute our syndrome, 10. What is the most likely code word? We locate the syndrome in the table. Now we go to the row, and the first element in the row is the most likely error. And of course, the element on the top of the column is the most likely code word. The problem with standard array table decoding is that it becomes infeasible when you have larger codes. So, for example, we will consider the 743 Hamming code, which is defined with this generator matrix and the parity check matrix. And of course, k is equal to 4. So now it means that we have 16 code words, which look like this. And the standard array table for this code looks like this. It's still small, but when you start having codes with n equal to 100 and k equal to 50, this soon becomes impossible to use. Or I should be more precise. of course it's possible to use, but it's too expensive in terms of latency. So basically the time that you take by looking through this table becomes exponentially larger, while decoding should be something that we do in real time, and so it should be super fast. So when you have large codes, this is not something you can do. But for now, we will try to do it actually for the Hamming code with this poll question. So you have this Hamming code, and you receive the sequence 110, 1110, and you compute the syndrome and you get 011. Now, can you use the table to find the most likely transmitted code word and the most likely error? So remember, first you locate the syndrome in the last column, and then you take the row corresponding to the syndrome, you locate the received sequence. In this way, you distinguish a row and a column, and you can immediately find the most likely transmitted code word and the most likely error. Okay, excellent. Majority of you answered correctly. The answer is D. So we locate the syndrome row, and the element in the first element in the row is the most likely error. And then we locate actually the received sequence, and the top element of that column will be the most likely code word. So good job to 54% of you. All right, now we introduce very quickly the notion of dual code because it is important for quantum regression. So we saw already the generator matrix and the parity-check matrix of the repetition code. We can define another code if we simply swap them. So basically, I define a code with generator matrix equal to HR and parity-check matrix equal to GR. The code that I get by doing this is called the single parity-check code. It's a 322 code. In general, there is no rule on how the minimum distance changes from when you switch from a code to its dual. We know that the dimension will always be n minus k, and of course n remains the same. But studying the minimum distance is highly non-trivial, and mathematicians love to do it. But this property holds that because the parity-check matrix of one is actually the generator matrix of the other, you have the two are orthogonal. And dual codes are denoted with this notation. The dual is denoted with this notation, C perp. But let's move on with some more interesting stuff. LDPC codes, which of course they play a very important role even before then in quantum error correction, in classical error correction, where LDPC codes are used widely used in all the kind of sort of technology that you can think of. There is an LDPC code running, most likely. LDPC codes are characterized by sparse parity-check matrix, which means you have just a few ones and a lot of zeros. Simply means that. And the advantage, one of the advantages that they give, is that they can be decoded with low complexity iterative decoders. So we have already seen the standard array table decoder, which is an implementation of the maximum likelihood. And we saw that it scales exponentially with the size of the code. And we said that this is not sustainable. We want the decoder to be fast. And so in low density parity check codes, decoders actually are fast because they can be because it's a property of the thanks to the sparsity of the parity check matrix, we can design algorithms that perform decoding that are very fast. We will see an example later. And these decoders operate on graphs, in particular Tanner graphs. A Tanner graph is defined by a parity-check matrix. So here again, we have the parity-check matrix of the repetition code that we saw earlier. And we can define the Tanner graph in this way. We have two sets of vertices, And in fact, Tanner graphs are bipartite graphs. One set of vertices are called variable nodes, and we have a variable node for each column of the parity check matrix. So we have V1, V2, V3. And then the other set of vertices are called check nodes. We have one check for each parity check equation. So for each, basically for each row of H, C1 and C2. And then we have an edge connecting a variable node and a check node if the corresponding element of H is equal to 1. So in this case, the Tanner graph will look like this. So you see that V1 is connected to C1 through this one, but not to C2. V2 is connected to both C1 and C2, and V3 is only connected to C2. So this is how we define the Tanner graph. And here's an example of how the Tanner graph of an LDPC code actually looks like. In general, we will consider DV-DC regular graphs. What does it mean? DV is what we call the degree of variable nodes, and DC is the degree of check nodes. The degree is the number of edges that touch a single node. So in this example, each variable node you can verify that has 3 incoming edges, and so DV is equal to 3. And we use this notation N, this calligraphic N of V, to denote the neighboring checks of the node V. And conversely, the check degree is 5 because each check node is connected to 5 variable nodes. And with this N, we denote the neighboring variable nodes of this check C. So now we have the fourth poll question. What is the parity check matrix that corresponds to the following Tanner graph? All right, this one was pretty easy. And of course, the answer is B. So for instance, we can check few nodes. The first variable node is connected to C1 and C3. So we have 1, 0, 1. Same holds for V2 and so on. We have another poll question. For the code given by the Tanner graph below, the following statement is false. N is equal to 25 and this is equal to 5. The check degree is 3. N is equal to 25 and the Tanner graph is bipartite. And it's a regular LDPC code. All right, of course, the answer is B, because you can clearly see that the check degree is actually 5. So B is the false statement. Okay, let's move on. So let's see how we can use this Tanner graph uh, to design a decoding algorithm. And actually, it will be interesting to see how we can actually implement a decoding algorithm substantially different from the standard array table. So again, these are low complexity algorithms, which means they run very fast. Uh, More precisely, it means that the number of operations that the algorithm does scales linearly with n, with the code length. They operate on the Tanner graph. And in particular, we have an exchange of messages between variable nodes and check nodes. Uh, so we have iterations. We have an iterative algorithm. In each iteration, we have the variable nodes sending some messages to the checks and the checks sending some messages to the variables. And then we have an early stop condition that if the error matches the syndrome, then we claim that the decoder was successful and we stop. Otherwise, we continue until we reach a maximum number of iterations. So the algorithm we're going to see is actually very simple. It is called bit flipping, and it's probably the fastest decoder for LDPC codes that you can think of. So first of all, we initialize the variable to check messages. So we will use this notation ni. Uh, Ni is variable to check message from the variable j to the check I, and 0 it means the 0th iteration. And the value will be either 0 or 1. It's the received value from the channel. so yj. And the check to variable messages, we will call them me from check I to variable j at the kth iteration. And in this case, it's just the sum of the incoming messages. So this n of I, if you remember, these are the variable neighboring the check j or the check I. And we basically sum the values, the variable to check messages incoming to that check. This summation corresponds to the number of unsatisfied checks. So basically, the checks corresponding to syndrome bits equal to 1. And now we compute for the same k iteration, the variable to check message. It looks more complicated actually to write the formula than to do it. But basically, the message from the variable j to the check I is to flip the previous message if the incoming messages from the check. So these are the check to variable messages. So all the incoming messages to the variable j, we sum them. If this number is bigger than a threshold, that usually we set to be half, roughly half of the variable degree. So we sum the incoming messages. If the summation is bigger than the threshold, we flip the previous message. Otherwise, we leave it as it was. So now we have the sixth poll question. What is the check to variable message of a bit flipping decoder computed at the check node is in this example? So we have this check is connected to 5 variable nodes, and each variable node is sending a message to the check 0, 1, 0, 1, and 1. And remember, uh, the check to variable message is the sum, the binary sum in this case, of the incoming messages. So essentially, we have the binary sum of this number. This will tell us if the check is satisfied or not satisfied, essentially. We are simply computing the parity check equation. All right. So the answer was B because this symbol, again, denotes binary summation. So we have 0 plus 1 plus 0 plus 1 plus 1. So we have 3 basically, but in the binary field, since we have an odd number of ones, this is equal to 1. So this check will send a message equal to 1 to these variables, meaning that this check is not satisfied. Or in other words, the syndrome bit corresponding to this check is equal to 1. Or in other words, again, the parity check equation is not satisfied. And now, another poll question. What is the variable to check message of the bit flipping decoder in this situation? So in this case, we have the threshold beta is equal to 1. And the previous message, so the previous value that we had to the variable node was 1. And the incoming messages are 0, 1, and 1. So to compute the variable to check message, we sum. And this notice that here now we have the traditional or conventional sum symbol, which means that it's not a binary summation, it is an integer summation. So we sum these messages and we compare this sum with the beta, with the threshold. And if the summation is bigger, we flip the previous message. Otherwise, we leave it as it was. All right. The answer is C, 0, because we have 0 plus 1, which is equal to 2. 2 is bigger than the threshold. And therefore, since the previous message was 1, we flip it and we send a 0. Okay, so good job. And now we actually see how this works. We see the algorithm in action, uh, and we see how it how actually corrects the errors on a code word. So we consider this LDPC code, this toy example. As you can see, the matrix is sparse. All the numbers that you don't see are zeros. So imagine all this empty space is just zeros. So we have two ones in each column. So we had the variable degree is 2 and three ones in each row. So the check degree is 3. And here it is the Tanner graph. So now imagine that we have this received vector here. And the syndrome is like this. So computing the syndrome already means that we have computed the first check to variable messages. So for instance, we can see that this the first syndrome bit is 0 because we are remember we take the binary summation of the incoming messages. So we have the first message is 1, the second message is 0, and the third message is 1. So we have 1 plus 0 plus 1 is 0. And similarly, the second syndrome bit is 0 plus 1 plus 0. So this is 1. And because the variable degree is 2, we set beta equal to 1. So recall this is the in the first iteration, the check to variable message. This is what we just did. And now these messages are sent to the variable. So for instance, the first variable received a 1 from this check and another one from this check. So it has 2. And similarly for the second variable and all the others. Now remember, we compare this number, which is the number of unsatisfied checks for each variable, with beta. So it means that all the variables associated with the number 2 will be flipped. So I have highlighted the flips here in red. And now these messages are sent again to the checks. So now you can see that um, the second syndrome bit, for instance, now is 0 because it has 0 plus 0 plus 0. So now it is satisfied. So now only these two checks remain unsatisfied. And we, again, in the second iteration, we do again what we did earlier. So we compute the binary summation, and we have these messages here. We send them to the variables, and we have that only this variable node is involved in two uh, unsatisfied checks. So this message will be flipped. Actually, it is interesting because remember, we flipped it in the first iteration because originally it was set to 1. We flipped it to 0, and now we flip it back. But you can see that now we have an all zero syndrome. So it means that we have actually converged to a valid code word, and we can claim that the decoding was successful, and we simply stop. All right. So since we are running a bit out of time, maybe I quickly just mention the sum product algorithm, which is another iterative decoder, um, which is actually state of the art even for quantum error correction. It's based on the idea that we can compute the maximum likelihood bit estimate by marginalizing for all the other bits. And okay, I won't go through this explanation, but the idea is that now the messages that variable nodes and check nodes share are more complicated than simply binary summations and integer summation. For instance, we have again variable to check message ni. For the sum product is the product of the incoming messages from the checks. So we have this variable node here is sending this message to this check, and it is basically is the product of the incoming messages from these all the other checks. And similarly, the message that the check node sends back is some combination of the incoming messages from the variables. So you see the principle is the same, but the actual value of the messages changes based on the specific type of iterative decoder that you have. So what I thought was a bit more important to introduce is how to actually run a simulation, how to run a Monte Carlo simulation, how to see how your decoder and how your code is correct, how much is correcting. And I will do it for classical error correction, but it is very similar. Actually, the concept is exactly the same, actually, for quantum error correction. So with Monte Carlo simulation, we want to estimate the performance of our code and of our decoder. So because it's not something that we can do by simply doing deriving mathematical formulas. It is a random process. We do repeated random sampling to obtain numerical results. And of course, the simulation software needs to be very fast to do this because you need to collect a huge number of samples to get an accurate estimate. So generally, your Python code won't work. If you're doing some serious simulation, you will need to write your code in C or C++ or something like that. But basically, the template for a Monte Carlo simulation is the following. You choose an error model, which can be, for instance, our binary symmetric channel. And you choose a code and a decoder, which can be, for instance, our LDPC code with our bit flipping decoder. You fix the number of samples to be large enough, and you fix the parameters of the error model. For instance, you fix your probability of error, your alpha. And now you generate a lot of samples. For each sample, you generate a code word, you generate a random sample of noise, you compute the syndrome, you run the decoder, and then if your decoder fails, you count a failure. At the end, when you've done this for all the samples, you simply divide the number of failures for the total number of samples and you get your probability of error. Now you repeat this for a range of probability of errors, a range of different alphas, and you get your error rate plot, which will look like this. So on the x-axis, you will have actually, I think this plot is more explicative. On the x-axis, you have your probability of error for the binary symmetric channel alpha. In this case, it goes from 0.001 to 0.01. And on the y-axis, you have your error rate given by your code and your decoder. And this curve actually tells you how your code is performing. Uh, you can clearly distinguish two regions. A region where actually by decreasing your alpha, your code is correcting more and more. This is called waterfall region. And then a region where somehow the performance stops improving. And this is called error flow region. And a big deal is actually to reduce this error flow. And this is done to specific mechanics that happens in the decoder. We're not going to go deep into it. But basically, your plot will look like this. And as Narayanan will say, will tell you just in a moment, and will show you, um, error plots, Monte Carlo simulation plots for quantum error correcting codes actually will look pretty much like this. Um, and of course, I think knowing how to run a simulation is very important. Um, But in any case, so I'm done with my section. So we're done with classical error correction, and now we will continue with the juicy part of this lecture. So thank you for your attention.
Thank you very much, Michele, for the nice introduction to classical error correction. If you have any questions, you can post it in the Q&A. I think we have some time, so let's take a 5-minute break, and then we will resume the second part of the course, where it will be an introduction to quantum and quantum error correction. See you in 5 minutes. Okay, let us resume the course. Can you hear me, Michele or Sijie?
Yes.
Okay, sounds good. So let us, so this second part of the course will be on an introduction to the basics of quantum and quantum error correction, and we will see how it relates to the first part that Michele just presented, and then we will use the quantum error correction for doing some quantum networking tasks in part 3 of the course that CG will present. So as always, you can always ask questions in the Q&A, and either Sijie or Michele will answer you. So let's proceed. So overall, in the first part, what we understood was, if you have bits, which I'm representing using a gray sphere here, and when they have errors, you have these kind of red spheres, and your job is to identify which of these red balls are. But it makes it much easier if you encode it into a code, because now the qubit or the bit is not on its own, but it's kind of correlated with everything surrounding it, so that if only one of it is an error, then you can use the correlations. You can do some checks, which is basically the syndrome you computed. And using the checks, you can identify which one went wrong and then go and fix it. So it's kind of like saying united we stand, divided we fall. So like Michele said, we will later come to the surface code and quantum LDPC codes, and we will look at error rate plots, and they can look something like this. So this might look like it's kind of flipped from what Michele showed you, and that's because the x-axis is still like your kind of the binary symmetric channel. This is like your physical error rate, but the y-axis, sometimes people plot what's called time to failure, which is kind of like saying how long the code stays alive without having to face a logical error or a block error. So it's kind of the opposite of what Michele was plotting as the logical error rate. And so here we see that there are many curves. These correspond to different code distances. And what you can see here is that as you keep increasing the code distance, the time to failure increases, which is a good sign, which means the higher the distance, the better your code is performing as you expect it to. But this only happens on one side of what we call the threshold. And so we will get to this when we get to the surface code, but this is kind of the typical performance plot that you will see in quantum mechanics. So let's start with the basics. So big picture. So in quantum computing, just like in classical computing, you will be familiar with NAND gates and NOR gates, and you know that they're universal for Boolean logic, which means any Boolean circuit and any binary function can always be expressed as a sequence of NAND gates and NOR gates. Similarly, in quantum computing, in a universal set of gates are given by this Hadamard, this T gate, and this so-called control NOT gate. Which means that any operation, any quantum unitary you want to implement can always be expressed as a sequence of these gates. And so what actually happens in hardware is, let's say you have some number of qubits where you're storing some quantum information initially, and you want to perform a logical operation, which could be an algorithm. So if you want to do, say, Shor's algorithm to factor a large integer, that's kind of a circuit that you want to implement, which will take you to a final state. But because the hardware is noisy, you're not guaranteed that you will reach the state that you want. So you could be wrong at the end of the computation. And you want to be able to fix that. And this is why you take qubits, say k qubits, just like we took k bits in the classical case, and you encode it into n qubits. So this is your nk code. And after you encode it into n qubits, where n is significantly larger than k, then you can do all these physical operations in the lab, which will also be noisy, but you can make them fault tolerant because now you're doing it on the code, and the code gives you some error protection. And so you do physical operations on the code, and you get to a final state, which is also encoded. And then hopefully, if you were able to fix all the errors, then when you decode, you will get to the state that you want. So this is kind of the longer path we take in quantum computing or networking, where the encoding and decoding gives you some error protection. So this course will focus more on quantum networks. So we will not get as much into the quantum computing aspects, except for the necessary concepts. So let's look at some of the basic gates that you can do, or basic operations, which we will also think of as error operations. So here, the quantum bit flip, or the quantum NOT gate, is represented as the Pauli operator X, where if you take a computational basis state, so this is read as ket0, K-E-T. So ket0 and ket1 are basically length 2 complex vectors, which form the standard basis. So ket 0 will just be 1, 0, and ket 1 will just be 0, 1. So these are just length 2 vectors, but we don't need those details for this. So I'm kind of hiding the actual linear algebra and the vectors. But basically think of ket 0 and ket 1 as the basis states. And so the X gate, the poly X gate, will flip 0 to 1 and 1 to 0. So this is called the block sphere representation, where typically we put ket 0 at the top and ket 1 at the bottom, and then X represents a 180-degree turn by this axis. Similarly, so this is kind of, it kind of feels like classical because you're just flipping 0 to 1 and 1 to 0. But the purely quantum operation here is the phase flip, where 0 remains as 0, but ket 1 picks up a phase -1 when you apply the Z gate. So in the block sphere again, we have to kind of rotate the axis. So this phase flip represents a rotation by the Z-axis, by the vertical axis. And this plus and minus are just 45-degree rotations of the 0 and 1 states. And the bit phase flip is a combination where you have 0 flipping to 1 and 1 flipping to 0, but you also pick up phases where I is thus the imaginary number. So I remember that I is square root of -1. This can also be represented in the block sphere. Now, given these three basic poly operations, so these are called poly operators, x, z, and y, and also the identity. As all of these operators are basically 2 by 2 matrices acting on these states, which I already said are length 2 vectors. So this is just matrix vector multiplication that's happening here. Nothing fancy, but I'm not showing you the matrix vector computation because it's not essential for this course. Okay, now we have already seen the binary symmetric channel in part 1 that Michele presented. Now the quantum version of this symmetric channel is where you start with an arbitrary input state, which is a linear combination of the 0 state and 1 state, where alpha and beta are complex numbers, such that magnitude of alpha squared plus magnitude of beta squared is 1. So this state has kind of norm is 1. So if you start with an arbitrary input state and you send it through this quantum symmetric channel, or more popularly called the depolarizing channel, then the result is either the input state itself with probability 1 minus epsilon, or it could apply one of these three poly operations, x, z, or y, with equal probability epsilon over 3. So the binary symmetry case, 0 became a 1 or 1 became 0. In the quantum case, the state gets applied by a poly error with equal probability. Okay, so let's do the first poll question for this part of the course. So you have the bit flip, the phase flip, and the bit phase flip. Can you answer which of the following is true? Can y be expressed as a combination of x and z or not? And if it can be expressed, which one of these options are correct? Okay, I think the majority of you got this right. So just to be clear, y is a combination of x and z indeed. And the right way to express y is as I times x times z, because when you first apply z to the input, you pick up this -1. And then if you apply x to it, then the 1 becomes 0 and the 0 becomes 1. And then you just have to multiply with I. So you can kind of see that this is basically applying z first to the input state, which picks up the -1, and then applies the x, which changes 1 to 0 and 0 to 1, and then applies I. So option C is the correct answer, as majority of you answered correctly. Now let's go to more than one qubit. So when we have more than one qubit, we can apply different poly operators to each qubit. And mathematically, we represent this using the tensor product or the Kronecker product. And for simplicity, sometimes we might just put subscripts for x applied on the first qubit, z on second, y on third, or sometimes we might just write a poly string, and it's kind of assumed or understood that this is applying different poly operators to different qubits. So this is not a multiplication, but this is just a poly sequence on a set of qubits. So the poly group formally on n qubits is given by all possible tensor products of I, X, Z, and Y. So tensor products like this. And then it can have a global phase, which is a fourth root of unity. So that's the group generated by the Pauli operators. And when you have many qubits, each qubit can have I, X, Z, or Y. And so there are 4 to the n possible Hermitian operators. So X, Z, and Y are Hermitian, so that they form an orthogonal basis for all matrices. So even though Pauli matrices are special, they actually form a basis. And the basis is with respect to the so-called Hilbert-Schmidt inner product, also called the trace inner product. So if you have two matrices A and B, the inner product between A and B is defined to be trace of A Hermitian transpose times B. So with respect to this inner product, you can check that all these Pauli matrices are orthogonal. They will have inner product 0 between two different Pauli matrices, and the group is generated by the individual Paulis on all the individual qubits. Now, what's the structure of the Pauli group? It's basically whether the matrices commute or anti-commute. So in circuits, you will see these Pauli operators represented using these boxes labeled with the notation for the Pauli operator. And here are the commutativity and anti-commutativity relationships. So one thing to keep in mind is when we write circuits, time goes from left to right. So you start with an initial state here, and then the state goes through X first and then Z. But when you write it in the matrix acting on the state, you go from right to left, which means there is a state psi. It first gets applied by X. It gets first applied by X, then applied by Z. And this commutativity relation tells you that this is equivalent to first applying minus. So first applying Z and then applying X, and then having an overall negative sign minus. So overall, this says that Z and X anti-commute. So if you change the order, you have to put a minus sign. Similarly, if you change the order of Y and X or Z and Y, you have to put a negative sign at the beginning. So that's the essential structure of the Pauli group. Now, when we go to more than one qubit, so here I'm showing 2 qubits, where on the first qubit, I'm applying X followed by Z and the same on the second. And we know that individually, they can be written using this relation. But now these two negative ones basically multiply and cancel out. And so you get that the sequence of 2 operations on the 2 qubits actually commute. So in the matrix notation, we will use the property of the Kronecker product that if you have A Kronecker B times C Kronecker D, then you can actually multiply the corresponding components, A times C Kronecker product or tensor product with B times D. So if you have a product like this, so here I have first X tensor X and then Z tensor Z. So in the matrix form, it's the opposite order. So you have Z tensor X times Z tensor Z times X tensor X, and you can multiply the corresponding components, and then we know that they anti-commute, but then the minus signs multiply and cancel out, and you get that the 2 matrices commute. So when you have more than one qubit, Pauli operators can commute, but in a single qubit case, they anti-commute. All right, now let's do something interesting using this. So what we call as stabilizers are basically commuting Pauli operators. So we just saw that X tensor X and Z tensor Z commute. So you can actually form a group that is generated by these 2 operators. When I say a group, the elements of the group are given by these generators, but also their products. So if you multiply XX and ZZ, you can check that you will actually get minus YY using the relation we saw in one of the previous slides, that Y is I times X times Z. You can easily derive that this is minus YY. And then, of course, if you multiply XX with itself or ZZ with itself, you will get identity. So these are the 4 elements in the group, but it's generated by these 2 generators, which commute. So this is called a stabilizer group. Now, an important result in linear algebra is that when Hermitian matrices commute, then they can be simultaneously diagonalized. So you might have heard about singular value decomposition or eigenvalue decomposition. So when we say they can be simultaneously diagonalized, it means that the commuting matrices have the same basis, same common basis of eigenvectors. So this is an important result, and this is kind of the key math that we need for quantum error correction. So once you have this particular stabilizer group, you can simultaneously diagonalize these two operators because they're Hermitian and they commute. And the eigenbasis turns out to be this famous state of Bell states. These are the 4 Bell states. So when I write 0, 0, it actually means ket 0 tensor product with ket 0 plus ket 1 tensor product with ket 1. So we already saw that ket 0 and 1 are length 2 vectors. When you take this tensor product and add, you will actually see that these Bell states are length 4 vectors. But that's kind of behind the scenes details. So these 4 Bell states form the common eigenbasis of these two commuting operators. So that's the key. And you can actually work out what the eigenvalues are. So for example, if you take xx, which is this operator, and you apply it to the first Bell state, you can use this Kronecker product property that A tensor B times C, so this property, and then you apply x to the first qubit and then x to the second qubit. And by linearity, you do the same to the second part of the superposition. Then you see that x will flip 0 to 1 and 1 to 0. But you see that this just exchanged the two states with a plus sign in between, which means you get back the same state that you had. So overall, when you apply xx to the first Bell state, you just pick up an eigenvalue of +1. So you see that phi plus is a +1 eigenstate of x tensor x. So, and similarly, you can work out the eigenvalues for all the other states and kind of prove to yourself that these are indeed common eigenstates of all these operators. So once you have a stabilizer group and you have simultaneously diagonalized them and found a common eigenbasis, then you can actually define a stabilizer code, which is defined as the subspace spanned by all the +1 eigenvectors of the stabilizers. So here we saw that phi plus is a +1 eigenvector of xx, and you can check that phi plus will also be a +1 eigenvector of zz. So phi plus will belong to this subspace. So in this case, we only get a one-dimensional subspace because only phi plus will have a +1 eigenvalue with both xx and zz. The others will have a +1 eigenvalue with one, but a -1 with the other, or both being -1. So let's get a little bit of practice doing this with this poll question. So you have all the details you need on the left side. So this is how you compute the eigenvalue for the state when acted by one of these operators. So can you do this math and say what are the eigenvalues of the psi minus state? So just to be clear, psi minus is 0, 1, minus 1, 0. So just apply xx and zz to that state and find out what the eigenvalues are. Okay, I think many of you got it right. Maybe there was some confusion with the eigenvalue for the first one, but you can double check that if you apply xx or zz to this psi minus state, both of them will pick up a negative sign. And so the eigenvalue for both xx and zz are -1. Okay, so now we have some idea of what Pauli operators are and how they commute or anti-commute, and how when you have many qubits, you'd use this tensor product structure. And we identified how to find when they commute, and using that we define stabilizer groups. And from stabilizer group, we saw how to define a stabilizer code. Now, in the previous example, we didn't get an interesting code because there was only one state, phi plus, that had a +1 eigenvalue with both xx and zz. Now we are going to kind of make more space to have actually a subspace that is more than one-dimensional. So how do we do that? So let's take the stabilizer group we had, but let's remove one of these operators. So let's remove XX and only define a group based on ZZ. So this group has a single generator, so it will only have two elements, the identity and ZZ. Now, once you have removed, we use the same definition for the code, which means we want to find all the states that have a +1 eigenvalue for ZZ, right? So we only want the subspace spanned by the +1 eigenvectors of ZZ, which means you just check that psi minus has a -1 eigenvalue, so that automatically gets removed. And similarly, psi plus will also have a negative eigenvalue. So both of these get eliminated. So the subspace that you're left with is spanned by phi plus and phi minus. So you can encode an arbitrary single qubit state, say alpha 0 plus beta 1. You can encode 0 to phi plus and 1 to phi minus and take linear combinations. And that gives you a subspace to encode and store 1 qubit worth of information, right? So this subspace has dimension 2. So hopefully this part is clear. So we took a stabilizer group. We made space by removing a stabilizer. So with 2 qubits and 1 stabilizer, you only have 1 constraint, and that constraint is that your eigenvalue for the subspace should be +1. And so ZZ acting on any of the encoded states should have eigenvalue +1. And then we saw that the subspace can be spanned by phi plus and phi minus, or in this case, equivalently by 0, 0, and 1, 1. Just a change of basis. But you do have a subspace that can store 1 qubit worth of information. Okay, so this is how we identify K. So K is 1 logical qubit here, and you're encoding it into 2 physical qubits. So this is now we are getting into this error correction mode that you saw in the first part. We have our first parameters N and K. So here is how you would do it as a circuit. So here is a circuit to actually encode. So the encoded version looks a little different because it's 0, 0, and 1, 1 instead of phi plus and phi minus. But like I said, it's just a change of basis. So this is one way to encode. This is the C0 gate. And you can check that alpha 0 plus beta 1. And if you start the second qubit in the 0 state and you do a C0, then it will do exactly this. So this is an encoding circuit for the code. And then we can see how do you manipulate the information. So initially you had this 1 qubit, but now you encode it into 2 qubits. But let's say you wanted to manipulate this information. Let's say you want to flip 0 to 1, which means you want to apply an X. So in the logical qubit space, you can just apply an X and you will get what you want. But after you have encoded, this is what you have in the lab. You could have like 2 atoms or 2 ions or 2 superconducting qubits that represent these 2 qubits. And those are the only ones you can act upon. You don't have direct access to this encoded information. You only have access to this physical qubits. So what do you do to the physical qubits so that the logical information get acted upon by X? Okay, so that's the idea here. So if you want to do an X on the logical information, it turns out that you have to do X on both qubits so that you flip 0, 0 to 1, 1 and 1, 1 to 0, 0. And that is exactly the encoded version of this state. So this is the XX is the logical X operation. That's what we call them. These are the logical poly operators for this code. So if you do XX physically, then you do X logically. Similarly, if you do a Z on either of the 2 physical qubits, you actually end up doing a logical Z. And logical Y is just a combination of the 2, right? So this is a very important concept, where once you have constructed a code, then you have to take any logical operation you want, and you have to encode it and find the encoded version. And then to denote the encoded version, we put a bar on top. So these are physical operations on the physical qubits that induce a logical operation on the logical qubits. And this is the idea of synthesizing logical operators, which means you have to translate a universal set of gates. So remember, in one of the first slides, I showed you this diagram where you had the Hadamard, T, and the C naught, and we showed how to encode k qubits into n qubits, do fault-tolerant gates, and then decode. And so an important part of that is to translate logical operations to physical operations. And this slide is showing you how to do that for the logical poly operators X and Z for this simple 2-qubit code. Okay, so now let's test the understanding for this. So here is the definition of this 2-qubit code and its logical operators. Now, can you use the commutativity relations we saw earlier and say which of these options is correct? Okay, we have a tie between B and C. So you're correct that X bar and Z bar clearly anti-commute. So you have X tensor X, and you can pick Z tensor I or I tensor Z. Either way, there is only one Z and X that anti-commute. The X and the identity commute, and therefore X bar and Z bar definitely anti-commute. But maybe this was tricky. But if you check, X bar and X bar is XX and ZZ, they commute. We have already seen that earlier. And then you can also check that ZI or IZ, Z commutes with Z. Therefore, the logical Z operator also commutes with stabilizers. And this is a general principle. So whenever you have a pair of logical operators on the same logical qubit, they have to anti-commute, but all the logical operators must commute with all the stabilizers. Okay, so the answer in this case is C. So hopefully you can double check your calculation and convince yourself that this is true. Okay, let's move on. So we have this definition of this 2-qubit code. Now we already saw that poly operators form an orthogonal basis, which means any matrix can actually be written as a sum of poly matrices. And this is kind of the reasoning behind why we consider only poly errors, right? So we defined this depolarizing channel initially, where a qubit gets acted upon by identity or X, Z, or Y. And the reason we don't typically talk about more general errors is because any error can be broken down into poly errors. But there are caveats, there are subtleties, so that's why I put a star here. But as a first principle, that's good enough. Okay, so let's see what happens when a poly error acts on an encoded state. So let's say you have an encoded state psi bar, this alpha 00 plus beta 11, and let's say the channel applies an X error on the first qubit, which means 0 gets flipped to 1 and 1 gets flipped to 0. So this is the state that you have. Now your job is to figure out whether an error happened, and if so, then how do you fix it? Now, the parity check in the quantum case, so the classical case, Michele told you, that is this parity check matrix H, using which you can compute the syndrome. So if you have a received vector Y, you can do Y times H transpose, and that will give you your syndrome. In the quantum case, you cannot do that because there is no received vector, because this state that you have is in your physical system, and you don't get to see it. You don't get to see this superposition. It's just two atoms sitting in your system, or two whatever physical modes you have. You don't get to observe it. The only thing you can do is do measurements. But if you measure individual qubits, you will collapse the state and you will lose the superposition. So you cannot do that. The only thing you can measure are global properties of the state that don't depend upon the encoded information. So in this case, the encoded information was alpha and beta, right? 0 and 1 were just carriers, and they got changed to 0, 0 plus 1, 1. But alpha and beta is where the information is. So you shouldn't do anything that tries to ascertain what alpha and beta are, but you can measure common properties for the state that are independent of alpha and beta. And in our case, that means you can measure a stabilizer, ZZ, because the stabilizer does not depend on alpha beta. So if you measure the stabilizer on the original state, obviously you will get +1 because that's how we define the code. But now you can measure ZZ on this state and you will actually get a syndrome which is -1 because this is actually a negative eigenstate of ZZ. So in this case, what you will do is, every now and then in your system, you will measure your stabilizer and you will get a syndrome and you will pass it to a decoder, just like in the classical case. And the decoder sends you an estimate of the error. So in this case, it can send you an estimate which could be Xi or Ix, because Xi is the actual error that occurred and that matches with the syndrome. But Ix, if you flip the second qubit, that will also give you a -1 syndrome. And so you cannot distinguish between the two. Those are the two possible cases. But the thing to note, and we'll get back to this, is that the second error here, Ix, is actually the original error that happened multiplied by the logical X operator, which means if the decoder gives this as the answer, then you inadvertently also apply a logical operator and actually flip the logical information without knowing it, right? That's a problem. So this is what we call a logical error. But these are the two cases possible here, and we'll get back to this. Okay, so here is the encoded circuit again. Now I showed you how to measure the syndrome, but if you want to actually write it out and kind of convince yourself that this commutativity is what you need, here is how you can actually compute the syndrome when you're trying to simulate a code. So so let's say you start with the encoded state psi, and error applied is E. And now you're trying to measure the stabilizer, right? When you measure the stabilizer, you can apply the stabilizer and see what eigenvalue you get. So if I apply ZZ to this errored code state, and the error, for example, is X on the first qubit, then we know that this is a Pauli operator and this is a Pauli operator. And we know that they anti-commute. So if I change the order, I pick up a negative sign. But now the stabilizer acting on the state is the state itself, because by definition, the code state is a +1 eigenstate of the stabilizer. So this has a trivial action, and I can just remove ZZ. What I'm left with is just -1 with the error applied on the state. So overall, what did I get? If you compare the first and the last parts of this equation, we applied ZZ to the error state, and we got -1 times the error state, and that's an eigenvalue equation, right? So the eigenvalue of ZZ acting on this state is -1. And this is exactly how you compute the syndrome. You just take the error that got applied, and you see if it commutes or anti-commutes with the stabilizer. Okay, and then you pass this syndrome to the decoder, and the decoder tries to compute the most likely error that could have caused the syndrome. So like I said in the previous slide, this case would represent correct decoding, but if the decoder guessed Ix as the error, then that would be wrong, because the combination of the true error that got applied times the estimate from the decoder ends up applying a logical operator, which means you have flipped the logical information without even knowing it, and that's a problem, and that's what we call a logical error. Okay, with those concepts, let's test your understanding. Here's the next poll question. So I'm giving you a different true error, Z acting on the first qubit. So what is the syndrome that you obtain? What is the decoder estimate? And how is this error correctable? Maybe there was some, yeah, so this is a tricky one the first time. So let's think about this. So the correct answer is actually A. So let's see why. So the true error was Zi, and then the syndrome that we obtain is the commutativity of the error with the stabilizer. But the stabilizer is all Z's and the error is all Z's, so they will obviously commute. So the syndrome is +1. Okay, so this is why I guess many people did B rather than A. Both have the syndrome being +1. So I think maybe there was no confusion there. The confusion is what the estimate from the decoder would be. So the decoder sees nothing that went wrong, right? So then the syndrome is +1, It just assumes that everything was okay. There was no issue. And so there is no reason to guess that there is some non-trivial error that occurred because the syndrome is not -1. And when it's +1, it means you are in the code space. And when you're in the code space, the decoder doesn't guess anything that went wrong. So the decoder will guess that nothing wrong happened. So it will guess the identity. And in this case, that's not correct because the actual error went undetected because it never flipped the syndrome. So in this case, this error Zi is not correctable. And as you will note, Zi is actually a logical operator, which means the error actually flipped the face of the logical qubit, which goes undetected because you're still in the code space. Hopefully that is clear now. Okay, so this is only a trivial code, but we need a systematic approach. And we already saw that, classical coding is kind of well established and there's a lot of cool stuff like LDPC codes. So how do we make this connection between quantum error correction and classical error correction? So for that, we need a binary representation. So here is the binary representation we will use for Pauli matrices. So if you have a tensor product of Pauli matrices, we will denote it as E of two binary vectors A, comma B. The binary vector A represents the X component of the operator. So if you have an X, you put a 1. And if you don't have an X, you put a 0. If you have a Z, you put a 0. If you have a Y is a combination of X and Z, so you will put a 1. The vector B is the Z component. It's the opposite. So when you have an X, you put a 0. When you have a Z, you put a 1. And when you have a Y, it also has a Z in it. So you put a 1 there as well. So this is how you can translate a tensor product of Pauli matrices into a pair of binary vectors, one denoting the X component and the other denoting the Z component. Okay, so this is all nice. It's just a nice binary notation. But using it, can you actually say if two Pauli operators commute? So let's say you have these two Pauli operators, and clearly you can have this binary notation. So this one we already saw above, and this is a new one, but ZZX means there is no X's, so you put zeros, and there is an X at the end, you put a 1. And again, ZZ, you put a 1, 1, and the last one has an X, so you put a 0. So this is the X component, and this is the Z component. Now you have these two pairs of binary vectors, and you want to do some computation in the binary space that tells you whether the matrices actually commute. And it turns out you can actually do that. So let's denote them A, B, and C, D. The right thing to do turns out to be this so-called symplectic inner product. So we know that, for example, if you compare each location, if you have an X and a Z here, then clearly they anti-commute. So this one will pick up a -1. Z and Z commute, so there is no -1 there. But Y and X again anti-commute, so you should pick up a -1. So the idea is to compare the X component of one vector with the Z component of the other, and similarly the Z component of the first vector with the X component of the other, because those overlaps tell you how many times they anti-commute. And so that's what this computation does. It takes the X component of the first vector and overlaps it, computes the inner product with the Z component of the second, and similarly the other way around. And you add them all modulo 2. If you have an odd number of anti-commuting pairs, then you get a 1, and that denotes that the matrix is anti-commute. So in this case, if you do this computation, you will see that you get 1 plus 1 is 0, which means these two actually commute, which is true because X and Z anti-commute, Y and X anti-commute, and those two negative signs will cancel out. And so overall, the matrix is commute. So this is how you turn Pauli operators into binary vectors and compute whether they commute or anti-commute. So let's do a little bit of computation to make sure that you understand the notation. So you have two Pauli operators, XXX and ZZI. Can you write the binary notations and also compute the symplectic inner product? I think the poll should pop up quickly. Yeah, there you go. Okay, I think a majority of you got it right. So the answer is B. So I think the binary notations should be clear, and clearly XX and ZZ, they overlap on two places, and those two negative signs will cancel. And so you can do that in the symplectic inner product space and convince yourself that they are actually equal. Okay, so that's the binary notation for poly operators, and that is powerful because it now lets us represent stabilizers using binary vectors and then use all the classical coding that we saw in part 1 for doing quantum error correction. So here are, say, two stabilizers, ZZI and IZZ. Clearly, they commute. They act on 3 qubits and they commute, which means they have a common eigenbasis, and that would define a code. So that's the idea behind this example. Now, if you take the binary notations and you stack them up into a matrix, you get a quantum parity check matrix, right? So there is no X component in both of them. The first half of 0. The second halves denote ZZI and IZZ. And this should remind you of the single parity check code that Michele talked about, which is the dual of the repetition code. So if you denote the halves as HA and HB, we know that stabilizers must commute, which means the symplectic inner product of the first row and the second row must be 0. And the way to express that is using this equation. So HA, HB transpose and HB, HA transpose, when you add them, should be 0 modulo 2. So this is just doing symplectic inner product for all pairs of vectors in the rows of H. So here we only have 2, but if you have more, you can do this computation to check that it's a valid quantum parity check matrix. And we already saw that the syndrome is just the commutativity relation between the actual error and all the stabilizers. And so we know that the commutativity is given by the symplectic inner product. So the syndrome can be computed as the symplectic inner product of the error, which in this case I'm denoting as the pair of binary vectors C and D. You can take the symplectic inner product with each row of H, and that if you stack all of those binary values, that gives you the syndrome. And so here is the kind of matrix vector product to compute it. So I've swapped C and D because that's what the symplectic inner product asks us to do. Okay, so this is kind of how we will denote stabilizers using binary matrices. And so here is on the left is the 2-qubit code we already discussed. We can naturally extend it to a 3-qubit code. So if you start with this 3-qubit state, which is called the GHZ state, the Greenberger-Horn-Zeilinger state. And the stabilizers for this state would be all these 3 operators. And we make space for a code by removing a stabilizer like we did before. And we are left with ZZI and IZZ, which are the stabilizers I showed you on the previous slide. And then you can write an encoding map, you can write an encoding circuit, just all like the 2-qubit code. And in this case, the logical poly operators will be very similar to the 2-qubit code. So here is a 3-qubit code. But one caution is that even though the encoding looks like it is kind of the repetition code, it is not. So this is not the same as taking this single qubit state and copying it 3 times. You can actually check that that's not the same as this encoding. And in fact, there is the no cloning theorem that says that you cannot arbitrarily clone or copy any state, any quantum state, which means there is no control C in quantum. And so this is actually just a superposition of the code words of the classical repetition code, but it's not a quantum repetition code. All right, so now we have seen how to define a code, how to compute syndrome, and how to do all this in the binary world. But of course, in the lab, you build something using some physical systems, and you don't get to see what error occurred, and you cannot do commutativity checks, right? So you need some physical methods to actually implement this. And this is the stabilizer measurement circuits that we need. So here for this code, ZZ and IZZ, to measure stabilizers, you take the 3 qubits of the code, and then you have an ancillary qubit initialized in the 0 state, and then you draw CNOTs where the controls are on the data qubits and the targets are on the ancilla. And then you measure the ancilla qubit in the Z basis. And depending on whether you get +1 or -1, you can tell if the syndrome is +1 or -1. And the logic behind this is simple. Because, for example, let's say you take the same example as before. Let's say you have an X error on the first qubit. What actually happens is you can actually propagate this error through the circuit. And using circuit identities, which I won't talk about today, you can convince yourself that this X will propagate down the C0 and actually flip this 0 to a 1, right? And so it will actually flip, which means it will flip the Z outcome from +1 to -1. And that's the sign of the syndrome. And so this is very much exactly capturing what the commutativity check we did before does. And that's because if you have an even number of x's, so let's say you have x error on both the first and second qubit, so you'll have 2 x's passing down and they will cancel out, right? So basically you're just checking the number of times x propagates through these CNOTs, which is just computing the overlap between the error and the locations of Z in the stabilizer. And that's essentially a commutativity check. So if the error anti-commutes with the stabilizer, it means you have an odd number of x's passing down, and that will flip the syndrome. But if you have an even number of x's in the support of the stabilizer, then it will commute with the stabilizer and it will go undetected. The syndrome will be +1. And this is exactly what we do by checking for commutativity. So yeah, so this is how you would do it in binary. We have seen this before. But in this case, a Z error, because it commutes with all the Z operators, it turns out that it doesn't propagate through the C0. So the Z will just go right through the C0 and never go down, which means it will never do anything to the ancilla. And that's why it goes undetected. So this is how we define the third parameter of the code. So we've already seen N and K. The way we define the minimum distance of a code is as the minimum poly weight. So the poly weight of an operator is the number of qubits on which it does not apply the identity. So in this case, even though this is a 3-qubit operator, it really only acts on 2 qubits. So the poly weight is 2. So the minimum distance of the code is the minimum weight of an undetectable error, right? Which means the error does not flip any syndrome. And that's equivalent to saying it's the minimum weight of a logical operator. So in this case, the logical operators are exactly this. And these single qubit Z errors, like I said, will go undetected. And so the code distance is 1. Okay. So given those, now we know how to compute N, K, and D. So here are 2 errors, E1 and E2. You can do this either way. You can do this in the poly domain or you can do this in the binary domain. But either way, can you compute the syndrome and say which of these options is correct? You just have to check for commutativity of the errors with the stabilizers. Okay, maybe this calculation got tricky. So the actual answer is A. Let's see why. So you have XIX and your stabilizer is ZZI, right? So if you check for overlaps, so X on the first qubit and Z on the first qubit anti-commute. So that's one anti-commutation. I and Z commute. And then X and I commute. So this is ZZI. So there is only one anti-commutativity between the first X and the first Z, and therefore the first error causes a 1 syndrome, and so this is 1. So this is in the binary domain, so we're doing zeros and ones because we're doing symplectic inner products. And similarly, XIX will also anti-commute with the second stabilizer because it's IZZ, and the last Z anti-commutes with this last X. So XIX anti-commutes with both stabilizers. So both syndromes will be 1. And the same thing for IXI. The middle X will anti-commute with both the middle Z's. Therefore, both symptom products will be 1. And so both of these errors, even though they're distinct, they actually cause the same syndrome. So you cannot distinguish one by the other just from the syndrome. And you should recall what Michele showed with the repetition code, right? With the repetition code, we had these Hamming spheres. You had 0, 0, 0 and 1, 1, 1. And if you had only one flip, 0, 0, 0 becomes, say, 1, 0, 0, then you can correct it back to 0, 0, 0. But if you take 1, 1, 1 and the channel flip 2 bits to make it 1, 0, 0, then you will still decode it to 0, 0, 0, which is wrong. So the same thing here, instead of flipping 1 qubit, as in the case of E2, if the channel flipped the other 2 qubits, it turns out that the effect is the same. Meaning in terms of the syndrome, the effect is the same. But if this was the actual error, your decoder will actually take the syndrome and guess this to be the error, because a 1 qubit error is more likely than a 2 qubit error. But unfortunately, the combination of the true error and your correction, the product will become XXX, which we know is a logical operator for the code, and that will become a logical error. So this example is tricky, and I deliberately put it because I want you to see that these two errors will have the same syndrome, but they have a different effect. Now let's slightly change the problem. So now I've changed the errors to ZIZ and IZI. So this is the next poll question. Now can you compute the syndrome for both errors and say which option is correct? Hopefully this will be easier. Okay, I think this case the answer is D. So you can see that both of these are Z-type operators, and the stabilizers are also Z-type. So Z operators and Z operators always commute. So both of these errors will commute with both stabilizers. So the answer is D. And again, you can see here that E2 is a logical operator, and so it should have a zero syndrome, because every logical operator is an undetectable error. So if you take a state and if you apply a logical operator, you're just changing it to a new code state, right? So on every code state has a zero syndrome. And so whenever you apply logical operators, you're just moving within the code space, and that never changes the syndrome. The syndrome will always be trivial. And so in this case, this is a logical operator, and ZIZ is also a logical operator because it's just a product of ZI and IIZ. So both of these are just the logical Z operator, and they will go undetected. And so they will have a zero syndrome. And so they will commute with both stabilizers. Okay, so we have covered kind of the basics using this 3-qubit code, and it cannot really correct any X error, any Z error, because Z errors will go undetected. So Peter Shor came up with this brilliant construction in the 1990s, where he constructed this 9-qubit code as a combination of these the 3-qubit code that we just saw and its other version. So here, if you can identify that this is the encoding circuit for the 3-qubit code that we just described. So ZZI, IZZ, and these logical operators. However, before encoding into the 3-qubit code, he used the 3-qubit so-called phase flip code, right? So so you initially take a logical qubit and you encode it into 3 qubits using the same circuit, but at the end you apply this Hadamard gate, which basically changes the Z basis to the X basis. So the stabilizers for this orange part is actually XXI and IXX instead of ZZI and IZZ. So you first encode it into this phase flip code, and then you take each of the 3 qubits of the encoded state and then encode it further into 3 qubits using this bit flip code that we already defined. So this is what we call concatenation. You're doing 2 levels of encoding. You're first encoding into this orange block using the phase flip code, and then again into the using the blue block with the bit flip code. And so you end up with 3 qubits for each of the initially encoded 3 qubits. And so you get 9 qubits at the end. So this is a 9, 1, 3 code. So you're encoding only one logical qubit into 9 qubits. And you can check that the minimum weight of any logical operator for this code will actually be 3. So you can check that there will be 9 minus 1, 8 stabilizers. And where will the stabilizers come from? So we know that each of these 3 qubit blocks belong to this bit flip code. So naturally, ZZI and IZZ on these 3 qubits, similarly ZZI, IZZ on these 3 qubits, and ZZI, IZZ on these 3 qubits. So all of those will still be stabilizers. That makes 2 plus 2 plus 2, 6 Z-type stabilizers. Now the two X-type stabilizers, where do they come from? They come from taking this XXI and IXX, right? So initially, before the inner encoding into the bit flip code, if you only did the first stage, you will have XXI and IXX to be the stabilizers. But now you've encoded this qubit as a logical qubit of this inner code, which means the X that was originally on this qubit will become a logical X of this inner encoding. And the logical X for this inner encoding is XXX. So whatever was just X before will now become XXX here. Similarly, this X, the second X in XXI, will also get encoded into XXX. And therefore, this XXI stabilizer here will actually become X on the first 6 qubits in the inner encoded version. And similarly, the IXX will become X from qubits 4 through 9 in the inner encoded version. And that's where the two X-type stabilizers come from. So whenever you concatenate any operation on the first level of encoding will become a logical operation of the second level, and it will blow up into a bigger operator. And that's what happens with the X-type operators here. Now, another way to visualize this encoding, this concatenation, is that you take, you arrange your 9 qubits into 3 rows, and each row corresponds to a bit flip code, but each row actually encodes a logical qubit of the phase flip code. So this is another way to just visualize the same concatenation. But Peter Shaw realized that by combining the bit flip code, which can correct one X error, but which cannot even detect a Z error, and combining that with the phase flip code, which actually can correct one Z error, but cannot even detect an X error, you get best of both worlds, and you end up getting a code which can actually have distance 3, which means, remember the number of errors you can correct, which is T, which is D minus 1 over 2. And in this case, which is 3 minus 1 over 2 is 1. So this code can actually correct an arbitrary error on a single qubit. And it was the first error correcting code in the quantum case. All right, so now let's look at some other code examples. So Andrew Steen came up with the 7-qubit code using the classical Hamming code that Michele showed you. So here is the parity check matrix for the Hamming code. And the way you construct the Steen code is by doing this kind of block diagonal construction, where you take the same parity check matrix and make X stabilizers and Z stabilizers out of the same matrix. And for this to be valid, of course, you need to check that they commute. And if you do this commutativity check, you end up only needing to compute HH transpose, which in this case turns out to be 0. And you can check that for yourself, which means the X stabilizers and Z stabilizers that you define will commute. And so they define a valid code. And then the logical poly operators in this case, you can apply X on all the qubits and Z on all the qubits. And that actually does a logical X and a logical Z on the single encoded logical qubit. Now you might ask that it is a distance 3 code, which means, and 3 should be the minimum weight of a logical operator, but the logical operator here has weight 7, right? Why is that? Well, that's not surprising because you can actually take a logical operator and multiply by a stabilizer, right? So because stabilizers, when you apply to the state, they don't do anything. They just pick up a +1 and it doesn't change the state. So any operation you do physically, you can always multiply by a stabilizer and you're doing the same operation. You didn't change anything. And so here in this case, because we're using the same H matrix to define X and Z stabilizers, if you take the last row, this actually represents the stabilizer X3, X5, X6, X7. And you can multiply this all X operator for the logical with this, and that will cancel out 4 of these X's, and you will be left with the weight 3 operator, and that matches with the distance of the code. So it is true that the distance of the code is always the minimum weight of a logical operator. Okay, how do you decode the Stein code? Well, you compute the syndrome using the formula we already wrote down. And in this case, it's special because H has a special, this stabilizer matrix has a special structure, which means it turns out that you can actually compute syndromes for X errors and Z errors separately. And you can independently decode them. So you can compute the X syndrome as X, which is just a product of your Hamming code parity check matrix times the Z part of the code, the Z part of the error, and similarly the other syndrome. And you can run the decoder to correct either type of error independently. However, if the X and Z errors are correlated, then this will be suboptimal and you have to do something smarter, but we will skip that for today. So how do you decode? Just like we decoded the classical Hamming code, you will compute the syndrome, and you can use the standard array table to estimate what is the most likely error, which is the first column. And that's what the decoder will give you at the output. Remember, in the quantum case, there is no received vector, so you will not go and search for any specific received vector. You will only get a syndrome, and with the syndrome, you can directly look at the first column of the matrix of the standard array to find the most likely error, and then you will go and apply that error to fix the error. All right, so here's the next poll question. So you're given the key parameters for the code and the definitions for the logicals and the minimum distance. Yeah, so consider the set of all poly errors that you can correct using the standard array decoding. Then which of the following is true? Think about it carefully and think about what different errors in the standard array represent. Very good. I think many of you got it right. So the answer is indeed C, right? So if you have 2 errors in the set that are correctable with the same syndrome, then they should multiply to a stabilizer because that's what correct decoding means. If it's wrong, then they will multiply to a logical operator. Very good. So let's now move on and kind of formalize these things more generally. So here is the construction for the famous CSS codes. So you can take 2 classical parity check matrices, Hx and Hz, and you stack them as block diagonals, just like we did for the Stein code. But in this case, you're generalizing because the 2 H's need not be the same. You can have a different Hx and Hz. Just make sure that they are orthogonal to each other, because that's what you need to satisfy the commutativity property. So this will satisfy the commutativity property, and then you can compute the syndrome, like I said, independently for X stabilizers and Z stabilizers, and you can run 2 independent decoders. As long as the errors are themselves not correlated between X and Z, this is fine, but otherwise this will be suboptimal. You can still do it, but it's suboptimal. And the logical X operators and logical Z operators will satisfy commutativity with the Z stabilizers and X stabilizers. Like I said, every pair of logical operators on the same qubit, a logical X and logical Z on the same logical qubit will anti-commute, but all logical operators will commute with stabilizers. And the distance of the code is the minimum weight of any of the logical operators. Now, another way to kind of visualize CSS codes is using this kind of ladder. which I like to draw. So if you define two classical codes, Cx and Cz, with some parameters, then the dual codes represent the x stabilizers and z stabilizers. And those have, so the parity check matrix for Cx is Hx, and the span of the rows of the Hx matrix gives you the x stabilizers. And similarly, the span of Hz will be the z stabilizers. The logical x operators come from this modulo space of Cz after you have removed Cx dual. So you can check that Cx dual will actually be a subcode of Cz. So if you remove that, that's where you get the x logicals. And similarly, Cx modulo Cz dual will give you the z logicals. And then you can compute parameters from the parameters of the initial code. And this is the number of logical qubits you will have in the quantum code. And we call the CSS code a quantum LDPC code if Cx and Cz are classical LDPC codes. And we will see the construction of a quantum LDPC code shortly. Okay, here is the famous surface code, which is a quantum LDPC code. It's defined on a square grid where all these circles represent qubits and all these squares represent stabilizers or parity checks. So the blue squares represent Z-type parity checks, and red squares represent X-type parity checks. So what does the Z parity check do? It basically says that Z applied on all the nearest neighbor qubits fixes the state, right? So Z, 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 Z will be a stabilizer of the code. So anywhere you have this box, Z applied on all the nearby qubits, all the 4 nearby qubits will be a stabilizer. Similarly for X, X applied to all the nearby qubits will be a stabilizer. Now we need to check that X and Z stabilizers commute. So if you take this X stabilizer and this Z stabilizer, so this one applies X, 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 X. This one applies Z, 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 Z. So clearly they overlap only on these 2 qubits. But because they anti-commute twice, here and here, the -1s cancel and they commute. And so you can check that all the stabilizers of this code commute. So it defines a valid code. Now, what are the logical operators? So it turns out that a way to define a logical X operator is as X applied on all these orange qubits on a vertical line. And a logical Z operator will be Z applied on all these blue qubits on this horizontal line. And clearly, the logical X and logical Z only overlap on 1 qubit, which means they will anti-commute. And you can check that on any stabilizer, this logical X operator will overlap twice. So it will commute, and similarly, the logical Z operator will overlap twice with an X stabilizer, and therefore they will commute as well. So you can check that the definition of stabilizers and logical operators are all valid. So this defines a valid code. And so this is a 5 by 5 lattice. And you can check that it will have 5 squared plus 4 squared. That's the number of physical qubits you will have. But it encodes only 1 logical qubit. And the distance of the code is 5 because this is the minimum weight logical operator. And it has weight 5. And so the distance of the code will be 5. So this is the definition of a surface code. It is CSS because it has X-type stabilizers and Z-type stabilizers. So you can put it in that HX at Z form. Okay, now let's look at what happens when errors occur. So here I'm showing you a few examples of errors. So let's say you have an error on this blue qubit. Let's say it's a Z error on the blue qubit, which means it will anti-commute with the X stabilizer that's adjacent, right? And so this will only flip this stabilizer and it will not flip any other stabilizer. Now, if you have a chain of Z errors, you have a Z, 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 then this X stabilizer has 2 Z errors adjacent, and so it will commute with the stabilizer and it will not flip the syndrome. Similarly, for this stabilizer, there are 2 Z errors adjacent to it. So again, it will commute and not flip it. but this one has only one Z error attached to it. Therefore, it will anti-commute with the stabilizer and it will flag the syndrome. So when you have a chain of errors, only the endpoints will get flagged. Similarly, here is an example of a chain of X errors. So if you have a chain of X errors, then only the endpoints will get flagged. All the middle stabilizers will commute. Here I have a single X error, and it will flip both the adjacent Z stabilizers because both of them will anti-commute with this error. So this is how, when you sample errors on this grid, you can compute which syndromes are flagged. Now, how do you decode, right? So the decoding is done using something called as minimum weight perfect matching. So let's look at what that is. So to do that minimum weight perfect matching, we introduce these so-called virtual checks. So the virtual checks exist only for matching purposes, and we'll see what role they play. So let's say these are virtual checks. Now what I do is I take the checks that are actually flagged. So I'm only doing this for the Z errors, which flip X stabilizers. So I'm ignoring the X errors that flip Z stabilizers. That's a separate decoding graph. So this one, we take the two X stabilizers that got flagged. I have them here. I join them with an edge, and the weight of the edge is the minimum length of the path that connects them, right? So I count the number of qubits that I need to pass to connect one flagged X stabilizer with the other. So I have 1, 2, 3, 4, 5, 6. That's 6. I can also go this way. There was 1, 2, 3, 4, 5, 6. Sorry, I have to go 1, 2, 3, 4, 5, 6. So both of these paths will connect the two X stabilizers, and those two paths will be equivalent because they will multiply two stabilizers. And so the minimum weight of the path is 6. It basically says that if all of these 6 qubits are in error, then I will get exactly this syndrome. Okay, that's what this means. Now, why do the virtual checks exist? It's because these boundary effects can happen. So here, like we saw, there is only one error, not 6. There is only one error here that flipped this X stabilizer. So to capture that, I have this virtual check so that I can connect this virtual check to this true check that got flagged. And I can call the weight to be 1 because there is only one qubit that is flipped. And similarly, I do all the other virtual checks. I connect them. I write the weight of the path that connects the virtual check with the true check. Now, once I have this graph, my goal is to match this graph, meaning I have to match every true flagged check with either another true flagged check or with a virtual check. So I have to only find a unique pairing. And that's what I want to get from this. And the pairing should satisfy the minimum weight, meaning if I sum all the edge weights of the pairing, then that should be minimum compared to all the possible pairings. So in this case, we can see that if I paired this check with this check, that would be valid, but that would have a weight 6, which is large. Whereas if I paired this with this virtual check and this with this virtual check, I only get 1 plus 2 is 3, which in this case you can check will be the minimum weight of the pairings, of all possible pairings. Okay, so this is now my guess. So I'm guessing that this is the right way to pair, which means I'm guessing that this is a Z error occurred here. But here I'm saying that this gets paired to this virtual check, not this one, which means I'm guessing that these two qubits are an error, right? But this one causes a logical error because the actual error happened on this side, but I'm pairing it to the other side. So I will be applying Z on these two qubits to try and fix the error. But accidentally, what I would have done is the true error times my correction will actually be a logical Z operator, and I made a logical error. So of course, these events can happen. But the idea of error correction on the surface code is done using this minimum weight perfect matching. Okay, so I think that's kind of the last main thing I want to discuss, and so we'll accelerate and go to the third part of the course. So here is the curve that we saw at the beginning of this section of this part. So this is how you would simulate the surface code. Just like Michele said, you can just sample errors on this graph, compute the syndrome, run this minimum weight perfect matching, and see if you got a correct answer or if you have a logical error. And if you keep counting it, you can calculate the logical error rate or the time to failure. And you can do this for different distances of the code. And here the distance is just the length of the grid. So as you can see, there is a threshold. So if the physical error rate is less than about 15.5%, then as you increase the distance of the code, the performance gets better and it takes longer for failure. But if you're on the wrong side of the threshold, then actually increasing the distance hurts you and you do worse and worse. So this threshold is a critical change point. And for any family of codes, this is the indication that there exists a good region where you can keep increasing the size of the code and the performance will monotonically improve. You can learn more about this curve in this reference. All right, let's do one more poll question. We're almost there at the end of this part. So when does a decoder cause a logical error on the code after decoding? We just covered that. Okay. So there was some confusion between A and C. I can totally understand why that happened. In this case, the answer is C. So remember that once you get an error estimate from the decoder will always give you an error estimate that has the same syndrome as the error, because we say that the decoder has converged only when it matches the syndrome that was measured in the hardware. So option A will never occur as long as the decoder converges. But of course, if the decoder gets stuck, sometimes that also happens. So it's totally understandable if you answered A. So the decoder can get stuck, especially these iterative message passing algorithms can get stuck, and sometimes they don't give you an error estimate that matches the syndrome. Um, but um, but we say it's a logical error only when the true error and the error estimate multiply to a logical operator. Otherwise, we call it a decoder failure. So option A would be corresponding to a decoder failure. All right, so this is kind of some advanced details for those who might be interested. So the hypergraph product codes is a construction that Tillich and Zimmer came up with in 2009, which kind of generalizes the surface code formally into a graph product. So here are some details about it. I won't get into this too much. It's just so you know that these constructions exist. So these come from kind of products of two graphs. So visually, for example, you can take a repetition code, a classical repetition code, whose Tanner graph is given in the bottom. And you can kind of flip the bits and checks and make this other code, CB. And then the hypergraph product is basically whenever you have an intersection of a check with a check, you make a red check, which is an X stabilizer. If you have an intersection of a check and a variable, you make a variable. So you basically intersect checks on the vertical code with bits of the horizontal code, and the different intersections give you different things. So some give qubits, and some give X stabilizers, and some give Z stabilizers. And formally, this is the graph product that you get when you do these tensor products. And so it's a powerful construction. And the surface code can also be obtained as a graph product in this form. And then you can run iterative algorithms like bit flipping, like Michele said, but a more advanced approach is to use belief propagation, which basically is trying to do some marginalization on the graph. So with iterative decoding, some things to keep in mind is that there is no received vector, like I said before. It's purely based on the syndrome. And if you don't have correlations, you can run two independent decoders. But if you have, you should do something better. And for the depolarizing channel, if you have correlations, you can also do a non-binary decoder. So a typical error rate curve looks like this. Like Michele already told you, the decoding schedule also matters. So you can either update all the variables and all the checks at once. You can kind of do a parallel update, or you can do a serial update where you go in some sequence of these bits and checks, and that changes the performance. So here is a flooding schedule, kind of which flattens out earlier, but a layered schedule actually gives you a much lower logical error rate. So these details can matter. And error floors exist, like Michele already told you. And degeneracy is the property that two different errors can have the same effect on the code, right? When they multiply to a stabilizer, two distinct errors can have the same effect on the code. So you have more options to correct errors than in classical codes. So here are some recent exciting LDPC code constructions. There have been even further works after these. And so kind of the state of the art is most of the things about topological codes, these kind of surface codes is known, but they have large overhead because they only encode one logical qubit into many qubits. Whereas LDPC codes are great because they can actually have both K and D scaling linearly with N, which is powerful. But how do you do logical operations on them? And how do you get around these long range connections you need to get these good parameters? So for the surface code, everything was nearest neighbor. But for these good LDPC codes, you have to interact a qubit here with a qubit there to measure stabilizers. And these long range interactions are harder to do in hardware. And how does the scalability look like with these codes? These are all kind of active areas of research. So let's kind of wrap up with this final poll question. Maybe we can do this quickly, and then we'll go into the last part. All right, fantastic. I think many of you got it right. So it is all of the above. So remember, the number of C naughts in these syndrome measurement circuits depends on the weight of the stabilizer. And the more C naughts you have, the more chances of failure. So option A is important because the LDPC codes are sparse, which means they have small stabilizers, small weight stabilizers, which means syndrome measurement is easier. And I think the other two you already know. Okay, so to wrap up this part, we have seen what code parameters for quantum codes look like. We started with the bit flip code. We looked at an encoding circuit. We looked at syndrome measurement circuits. And this is what I was just saying. If you have many of these C naughts, then those C naughts can also fail and kind of confuse the syndrome. And so LDPC codes are good because the number of C naughts will be small compared to the size of the code. And that actually doesn't scale with the size of the code. And then when you have errors, you propagate errors to figure out syndromes, and then you pass the syndrome to a decoder, which is typically a message passing decoder, to find out what actually happened. So hopefully that gave you a good idea of classical error correction and quantum error correction, and how we use classical coding ideas in quantum with all the subtleties that come in the quantum case, like we don't have a receive vector and we have to work with syndromes and so on. Now, in the last part, Sijie is going to tell you how to use all of this in quantum networking and specifically for entanglement distillation. So I ran a little bit late compared to what I was planning. There is about half an hour of material left, but I know my part was also long, so I want to give you a little bit of a break. So maybe we come back again in 5 minutes, and then we'll have about half an hour before we finish the course. But if you have any questions, you can still ask it in the Q&A. Thank you for your patience. See you in 5 minutes. Okay, I think Sijie, if you want to get started, we can see your screen, but maybe you should move to the part 3.
Okay, hello, can you hear me?
Yeah,
All right.
go ahead.
Okay, so hello everyone. My name is Sijie Cheng, and I am a PhD candidate with Professor Rengaswamy at the University of Arizona. So after the first part, classical error correction by Michele, and the second part, quantum error correction by Professor Rengaswamy, I believe you already have a basic understanding of quantum error correction concepts. For my part, let's explore how to apply these concepts in real-world situations. Let's start with a brief overview of a 311-bit flip code. At the beginning, we have a quantum state. After encoding, we can get the coded state. If an error occurs, we can use the syndrome measurement to get the syndrome for error. Generally, if there's no error, the same quantum circuit can be used to get the sign for stabilizers. From now on, we will focus on using the biostate as a tool to demonstrate quantum error correction applications. In fact, it is similar to the 311 code, but we concentrate on just 2 qubits. The key difference is that we can send these two parts to different locations to create a biopair. Consider a biopair between points A and B. The measurement will break up the pair. However, because the pair is entangled, measure one part of the pair will cause the deterministic measurement result on the other side. For instance, if we have a biostate of 00 plus 1, 1, and A measures a part of biostate on X get plus 1, we can confidently see that if B measures the part of B measures his part on X, will also get plus 1. Here, plus state simply indicates a measurement on X resulting in plus 1. Interestingly, measure just one part is sufficient. The other part will automatically align to the same result without needing actual measurement. And these two situations are equivalent. In this part, since we focus on applications rather than the core mathematics or quantum mechanics, I feel there is a very interesting way to introduce it. At the beginning, let us use some symbols to represent our learning so far, as they can be extremely helpful in grasping the key ideas of error correction in quantum networks. At first, uncoded state without error will be represented by dots, and those with errors by stars. We can use the squares to represent stabilizer generators. Imagine this as a box. Imagine this is a box, and then placing an uncoded state inside, turn it into a coded state without error. Symbolizing the box's protective nature. A square with its corner cut off represents a coded state visire. Similarly, small squares will denote the sign for stabilizers, and their cornerless versions will represent the symbol for error. These cut corners mean estimated error. At the same time, we use different arrows to represent the classical channel without error, quantum channel without error, and quantum channel with error, respectively. Next, these boxes will denote syndrome measurement, decoders, and correctors. And then the wavelengths with dots means biostates. And then the wavelengths represent the biopair without error. And the dashed line for those with errors. And the double lines will represent the equality. Now, let's apply these symbols to some previously discussed concepts. Uh, First, given a stabilizer generators or stabilizers and a coded state with error, using measurement, we can get the syndrome for error. Second, given stabilizers, the sign for stabilizer, and the syndrome for errors, using a decoder, we can get the estimated error. Finally, if the estimated error matches the actual error, using correct quantum circuit, we can correct it to get the coded state without error. Okay, let's start. At the beginning, let us imagine a quantum network Here we have a bunch of quantum nodes, which could be computer, sensor, or whatever. To simplify, we will discuss a network with just two nodes and one-directional communication. This means we are transmitting a quantum state with information from one node to another through a quantum channel. If the distance is short, this is a very low probability of getting an error. However, as distance increases, channel noise intensifies, reducing fidelity and eventually leading to channel failure. Later, if we also want to do some quantum network operations, it will make the channel fail very quick. Therefore, we need a way to correct errors and increase the stability of quantum bits in the network. This process is known as quantum error correction. Let's go deeper. We will name one node Alice and the other Bob. If Alice sends an uncoded state through a noise channel, Bob cannot correct the error because the state information is already lost. Thus, encoding is essential. Therefore, once Alice has an encoded state, and she can select a series of stabilizers. After encoding, she can get the coded state and the sign for stabilizers. And then Alice sends the stabilizer generators and the sign for stabilizers and the signs to Bob through a classical channel. Upon which is assumed there's no error inside. Next, Alice sends the coded state to Bob through a noisy quantum channel. Upon receiving the coded state with errors and stabilizer generators from Alice, Bob can use a measurement quantum circuit to get the syndrome of error. Using the stabilizers, signs, and the syndrome for error, after decoding, Bob can get the estimated error. Finally, if the estimated error aligns with the actual error, Bob can correct it by using a quantum circuit to get coded state without error. Finally, the coded state can successfully transfer from Alice to Bob. Throughout this process, most noise in quantum circuits could be ignored except for the decoder, which is a core point for quantum error correction. A quick summary. The sending order is not important. Alice could send the quantum state through a noise quantum channel, followed by stabilizers and signs through the classical channel. And then Bob can use the decoder to estimate error and correct it to recover the coded state. Now, this is the first poll question. What is the primary purpose of quantum error correction in quantum networks? Okay, perfect. The answer is D. All right. The quantum error correction in quantum network means correct errors caused by noise and operations in the quantum channels or quantum networks to improve the stability of quantum bits. As I mentioned, the decoder is the core of quantum error correction. Ideally, it should work perfectly. However, there are two main problems that could lead to decoder failure, concurrently causing the entire channel to fail. The first problem is long distance. As distance increases, the coded state accumulates more errors, leading to what we call the decay problem. Once the number of errors is larger than the limit that the decoder can correct, it will fail. A typical solution is using repeaters. Between Alice and Bob, we can introduce a node called a repeater. Depending on the simulation, the number of repeaters can be different, but we will focus on a single repeater scenario. First, Alice sends the coded state and the classical information to the repeater, which can use the decoder to estimate error and correct it. And then The repeater forwards the corrected coded state and classical information to Bob. Finally, Bob can use his decoder to estimate error and correct it again, successfully transferring the coded state from Alice to Bob. In summary, because long distance could trigger the decoder failure, we can use the repeater to reduce the error correcting pressure on a single decoder by shortening the distance. Now, for our second poll question, what is the primary purpose of the quantum repeater? Okay, perfect. The answer is B. The goal for the repeater is to solve the decay problem. The rest of them are not the primary purpose. The second problem arises even the sufficient distance. Environmental factors can cause too many errors, leading to decoder failure. This is a problem we cannot fully solve. Thus, we need an alternative approach where decoder failure doesn't cause quantum channel failure. One solution is to perform decoding earlier than the actual communications. To understand this, let's revisit the properties of the biostate. At the beginning, Alice prepared a biostate and sent part of it to Bob through a quantum channel. Here, we assume the quantum channel is perfect. And then the parts is Alice and Bob form a biopair. The mathematical form is below. But I may not go deeper here. I'm not go deeper here for the mathematics. So importantly, if we have n biopairs and a series of stabilizer generators, after mirroring, we can get k coded biopairs and stabilizer signs. The stabilizer measurement doesn't break up the biopair, and the pairs were predicted by stabilizers. Furthermore, if we only do measurement in the S part, the Bob part will also follow the rules, and these two situations are equivalent. Based on this property, we can go to the next point, called teleportation. At the beginning, Alice and Bob generate several biopairs, and then Alice wants to send a coded quantum state to Bob. After the operation and measurement between the coded state and one of the coded biopair, Alice can get the classical information that shows the difference between the coded state and the coded biopair. And then Alice needs only to send this classical information to Bob. Based on this information, Bob can transform another part of coded biopair into the coded state that Alice wants to send. Be careful, we never observe what the coded state is, but the differences between the coded state and one of the coded biopair. During this process, we can use the biopair plus classical information to transfer the quantum state and the information in the classical channel, but not the quantum channel. This idea gives us a new way to solve the decoder fail problem. So first, in a noise quantum channel, we establish an imperfect biopair. Then, as with quantum error correction, Alice sends the stabilizers and their signs to Bob through a classical channel. Bob uses the decoder to estimate error and correct errors. If the decoder fails, the attempt is discarded. However, if successful, the biopair is retained. This process can improve the purity of the quantum state. When Alice is ready to transfer coded states, she only needs to send the relevant classical information to Bob. Using this information and the biopair, Bob can retrieve the coded state that Alice wants to send. In this part, because we need to do many times before the actual communication, and we only keep the successful part. We call it distillation. A quick summary. In real-time communications, if there are too many errors, then the decoder will fail. Because of this, we first use error correction before the actual communication to improve the purity of bit state. And then, for the real-time communications, we use this good bit state to do teleportation of the actual data. Now, for our third poll question, what is the primary purpose of quantum distillation? Okay, actually, the answer is C. The goal for the distillation is to improve the purity of quantum state. The rest of them are not the primary purpose. Okay, so next, let us go through how to do the distillation. Directly creating a bit pair between Alice and Bob through a noisy quantum channel won't allow Bob to correct errors, leading to failure. Thus, we apply quantum error correction. Starting with a bit state, starting with n bit states and stabilizers. After encoding, Alice can get k-coded bit pairs and signs. Because we use the bit state here, the encoder could be implemented by stabilizer measurement on bit state. And then Alice can send the stabilizer generators and the sign to Bob through a classical channel. Subsequently, Alice sends part of the coded bit pair to Bob through a noise quantum channel and keep another one. Upon receiving the other part of the coded bit pair with error and the stabilizer generators, after measurement quantum circuit, Bob can get the syndrome of error. Using stabilizers, sign, and the syndrome of error, after decoding, Bob can get estimated error. If the estimated error matches the actual one, Bob can correct it using a quantum circuit to get the coded state without error. Finally, they can form a perfect coded bit pair between Alice and Bob. In the end, let us sum it up. So first, quantum error correction. That means based on the classical information that include the stabilizers and sign for stabilizers, plus quantum state, we can correct the error in the noise quantum channel. Second, teleportation. That means based on the classical information that includes the differences between the coded state and the coded bit pair, plus a perfect bit pair. We can transfer the quantum coded state by using classical information. Third, distillation. That means based on the classical information that includes the stabilizers and the sign for stabilizers, plus the imperfect bit pair, we can correct the error in the noise quantum channel. We can do this once again and again to avoid quantum channel failure. Alright, so these conclusions our discussion for this part. And right, thank you. Any question?
Thank you very much, Sijie, for completing the course with the third part on quantum networks. So hopefully you all got to see, the key ideas of error correction from Michele's part, sticking with classical codes. And then we kind of developed some quantum formalism, some basics. And then we, using this kind of binary representation for Pauli operators, we were able to represent quantum parity checks as kind of binary vectors and binary matrices, and that really enables us to leverage all of the classical error correction expertise and apply it suitably in the quantum case. And then Sijie explained to you how all of this is all applied actually in a networking setting. So in a quantum network, the way you should think about it is the key role of repeaters is to enhance the distance. And what you actually try to do all the time is to generate entanglement and purify it, distill it, make it high quality entanglement. And that's where we use the quantum error correction. These are called kind of second generation repeaters. So you generate a raw entanglement, which will be noisy, which will be crappy. And then you apply error correction or other protocols to distill good bell pairs and good entanglement. And then once you have entanglement between different nodes, then they can just use teleportation to actually send information from one point to the other by consuming the entanglement as a resource. So once you have the entanglement, then any other quantum data you want to send, you don't have to send it directly. All you have to do is some local operation and then kind of do some classical communication with the other node, and the entanglement will automatically teleport the information for you. So this is how we envision quantum networks will be built. And error correction is a key part because the better the quality of the entanglement, the better the quality of the communication that you can establish. So, and you can kind of put this in context with all the other courses of the winter school that you might have taken. All of this has to be implemented using materials and using devices, and that involves all the other parts. And on top of all of this, you need kind of routing protocols, which hopefully you would have heard about in other courses, which tell you how to route entanglement from one point to the other. We didn't cover that part. We only talked about how to purify entanglement. But on top of this, you will have kind of the quantum analogs of say TCP/IP or these kind of internet protocols that we know today. These also have to be developed in the quantum case. So the Center for Quantum Networks has projects on all of these parts. And so that kind of wraps up the course. I don't see any other remaining questions in the Q&A. But if you have questions, you can find my email on the department's website, and feel free to email if you have any questions. I hope you found this useful. We look forward to reading your surveys on the winter school courses and seeing how useful this was for you. Thank you so much for joining, and thanks again, Michele and Sijie, for teaching the course with me. You all have a good rest of your day and have a good weekend.
See you everyone. Bye bye.